All right, welcome class. Do a quick review of a little bit of a complicated problem. Shows up now and again, not terribly frequently. The relative motion problem. Now the relative motion problem typically looks like two objects playing either catch up, one starting behind the other and drives faster to catch the first, or two objects racing, one finishes before the other. So it's one of these games where you have basically two objects at constant velocity, different constant velocities, and they're moving along a similar track, and you need to figure out different things like how far are they from each other, how far did each one individually travel, how much time did it take, which took longer, things of that nature. So this page in our notes on page 23 gets into it a bit, but you really need to see it live in action. So that's what I'm going to give to you right now. Now, one of the recommendations I have in the new version of the notes is as follows. That you have one column for your first object, one column for your second object, and a relative motion column. Since this is constant velocity, we'll be dealing with velocity, displacement, and time for each object, and also relative or between or compared for the two of them. Now, one thing we will not do over here, one little mistake in the notes, is we're not going to think of the relative velocity, the vector nature of it. So we're actually just going to erase away that little hat. And really, when we think of our relative, we're just going to deal with that as a scalar. Okay, let's get to it. First one we started looking at was about Andrew and Bart. So here you see your two objects. You have Andrew driving off at 5 meters per second. You have Bart driving off at 8 meters per second with some delay. So how do we deal with this? It's actually a fairly heavy problem in terms of just keeping track of the algebra, unless you pull on your VDT12R chart. R kind of looks like a 3. So let's check it out. So we have object 1, that could be Andrew. We have object 2, that could be Bart. And we have the relative between the two of them. Of course, we need the velocity, the displacement, the time for each of these. So what can we do? Well, in the process of filling out this chart, you may answer more than what the question asks. You may actually answer what both questions ask and then some. So let's do it anyway. Here we go. So Andrew, what do we know? We know Andrew is heading along at 5 meters per second. So we can come over here to Andrew's velocity and put a little 5 meters per second in there. We also know that Bart is traveling at 8 meters per second. Now, whenever you need to find the relative anything, you're essentially subtracting the two vectors. So whether it's 5 minus 8 or 8 minus 5, it doesn't matter. All we're concerned about is the magnitude of it. That comes out to a relative speed of 3 meters per second. Okay, cool, easy enough. Now, Andrew is 40 meters away by the time Bart gets going. Huh. All right, now that's a little something right there. How do we deal with that? Let me give you a little example here. So, this can be Big Bad Bart. Husky's playing the part of Bart. His tractor's going to play the part of Andrew. So, Andrew gets going. So, Andrew's already in motion. But we don't start the problem until Bart starts chasing. So, at this point, Andrew's moving along, and Bart is chasing, but Bart is catching up. So the question here, is the 40 meters what Andrew actually travels? Is it what Bart actually travels? Or is it something else? So look at this again. They're starting out 40 apart, and then they start going until Bart catches up. Now if you notice, we are quite some distance away from where we started out. Bart has gone farther, he's going faster to catch up, but there's no reason that either of their distances will be 40 meters. What is 40 actually is how they started 40 apart to how they ended 0 apart. That's their relative displacement actually. So the 40 is actually the relative. And once you have two members of a column, bam, we can start making use of V bar equals D over T. Now, maybe in earth science you did a little pyramid like this. You had a density pyramid. Since we're doing V bar as D over T so many different ways with the cross multiplication, you might like a little pyramid. if you rearrange it, the one that stands on its own when they're all multiplication, that's always the one that goes on top. So D will go here, V bar and T. So if some of you are familiar with this, well then you're familiar. If not, don't worry about it. Just solve it. Notice we have V bar, we have D, we can get T. Well, let's do it. T, of course, is going to be over here. T will be D over V bar, which in this case is 40 meters over 3 meters per second. It's actually 40.0. And that comes out to about 13.3 seconds. Oh, okay. Now the interesting thing here, you gotta use your brain a little bit. That time not only applies to relative, but that's actually the amount of time that each of them was driving once Bart started chasing. And that's all we really care about. The problem doesn't start when Andrew takes off. The problem really starts as soon as Bart starts chasing him. Now, we're going to be going after each other. We have relative motion. What's going on? So that 13.3 is actually the time that applies to all cases. 13.3 seconds, 13.3 seconds. Okay? And from here, can you figure out the displacements? Well, sure. This is the individual, like how far did Andrew go during that 13.3 seconds he was being chased? How far did Bart go during that 13.3 seconds during which he was chasing? So we're finding the D there, so for each of these, D equals V bar T, which for Andrew will just be 5 times 13.3. So that comes out to about, what's that, 65 and another, what's that, 1.5, so 66.5 meters. And Bart, 8 times 13.3, so the 8 and the 13 is your 80, your 24, this is your 104, 2.4, so 104, yes, 106.4 meters. Okay, and it works out actually. You see here, we have a little bit of a rounding issue, but you see here, this is 40 meters between the two of them. So that all makes sense. So the questions here, actually, they're all answered. We're done. How far will Bart have to ride to catch Andrew? Well, here it is. Again, we have some rounding issue. And how long did it take Bart to overtake Andrew? Oh, here that is too. Isn't that nice? So this is not so simple as just, there's the answer, write your formula, boom, done. You got to think a little bit. But if you work with this chart, start filling in to get the relatives across, and then start working the verticals with V bar equals D over T, you can actually get everything. So at this point, I'm going to jump over to W2.8, not page 1. Here's page 1. You should be okay with that. I'm going to jump over to page 2. Now you're going to choose how much you use this. That's up to you. But I'm going to go through each and every one of them. Like I said, this is not heavily tested in this course. But listen, if you like it, I'll make a 2.8b. You can go ahead and try them again with different numbers, different magnitudes. Let's try this out. So we have car A moving in a straight line. Here's its speed. We have, oh, it's 200 meters behind car B. Oh, there's its speed. How far before it catch? Oh, the catch-up problem. Catch-up problem is standard business, relative motion. So that is this problem again. They don't start even. The one in the back drives faster, and at some point it catches up. So there's lots of things you can ask about that, and the truth is, I'm not even all that concerned with the question. If I set up my chart, hopefully everything will just fall out. So object 1 can be car A, object 2 can be car B, and then of course we have the relative. And we need the V, the D, the T. Let's run this across. So what do we know, if anything? We know something. So let's go. So car A, 20 meters per second. Car B, I'm going to pick the easy ones, 15 meters per second. No matter which one's following which, the relative speed between them is, of course, then 5 meters per second. All right, good. Now, it's initially 200 meters behind car B. Well, this is just like the one we just did in the notes. So if it starts out 200 meters behind, here's car A, here's car B, starts out behind. it's going to move. They're both going to move as it catches up. But that 200 is not car A's distance. It's not car B's. It's actually the relative. So between them was 200, and that 200 ends up disappearing down to 0. That's actually their relative displacement that ends up covered. So here, 200 meters. Oh, look at that. We got 2 out of 3. And 2 out of 3 ain't bad, because we're looking for T now. From your equation, V bar is D over T. Maybe you want that little pyramid. Your T is then D over V, which is 200 meters over 5 meters per second. 200 over 5 gives you 40 seconds. Okay, now these two are driving for the same amount of time. In fact, that 40 seconds applies to all of them. So use your brain with the times. And now that you know it's driving for 40 seconds, oh, well, that's pretty easy here. All you got to do is get the D's. D is V bar T. Throw some D's on it. There we go. All right, so V times T. There's your 800 meters for cart A. There's your, what's that? 600 meters for cart B. 200 meter relative. Good to go. How far must car A travel? Well, car A itself, 800 meters. Done. There it goes. Can we do this with another one? I think so. So this actually, if you're starting to feel the flow a little bit, pause the video, try it, pull it back, see how you do. There are other ways to skin this cat, but this is really a clean, simple, somewhat uniform approach. If you start getting into the little details of V bar equals D over T for every little separate car and situation, it becomes a big mess. Lots of variables you have to follow. All right, so 2 bicyclists set off from the same point at the same time. All right. Bicyclist alpha rides at 14, beta rides at 12. So they start together. They go over the same course, but one is faster than the other. How much later? So now there's going to be a difference in time. How much later will bicyclist beta arrive? So these times won't all match. All right, let's see what happens here. Bicyclist alpha, bicyclist beta, and of course you get your relatives, V bar dt. All right, so what do we know? So alpha is at 14 meters per second. Beta is at 12 meters per second. Whether we need it, I don't know, we'll see. There's a 2 meter per second relative speed here. They both follow a 1 kilometer course. Okay, so each one travels 1 kilometer. Now notice, this 1 kilometer, I'm going to adjust because this is in meters per second. So you can do it all in kilometers, but this says meters over here. So let's put it all into the same base unit. So this is 1,000 meters, so is this. How much later will bicyclist beta arrive at the finish? Now we're talking about times, but check this out. We got some action. So the time here, well, time is going to be, do your quick rearrange, that's D over V bar. And so in the first case, that's 1,000 over 14. Double check that one, make sure I'm not a little bit off. 1,000 over 14. And you get about 71.4 seconds. The other one will be 1,000 over 12. And there's your 83.3 seconds. Okay. And so if it takes this one 71.4, it takes this one 83.3, well, how much later will it arrive? What's the relative times between them? You're just doing a quick subtraction over here. And so the relative times from 83 to 71 is about 12, but we lose a 1 there. You're talking about 11.9 seconds. There's your answer. Okay. So, again, this is not an overnight learn, but you just see more of it, live more of it, feel more of it. Let's try it out over here. Oh, we got Steady and Husky, our old friends. They're going to decide whether, settle whether slow and steady really wins the race. Fan cart, dainty fan cart will be the impartial observer. All right, poor Husky still has heart pain. All right, so let's check it out. So what's happening here is Husky's getting a head start, and they both reach the finish line at the same time. So this is looking familiar now. So it's this to this. It's not the third time you're seeing a problem like this, but you may not be actually solving for the same physical quantity. So here we go. We can have steady, we can have husky, and then relative between the two of them. V bar, D, T. What do we know? Well, let's check it out. All right. So they both arrive at the finish line, which is 2 meters away, at the same time. So they each traveled 2 meters. Now, Husky traveled at 0.15 meters per second. And they also say that Steady gave Husky a 5-second head start. That means Husky is driving for 5 more seconds than Steady. That by itself, that's a relative time there. That doesn't tell you about their individual times yet. So can we figure anything out? Well, sure we can. Check it out, 2 out of 3. So we're trying to find T for Husky. T is going to be D over V bar. And in this case, that's 2 meters over 0.15 meters per second. So 2 over 0.15, what do we get? 13.3 seconds. Okay, now how can we do something with this? Well, we know Husky took longer. And here you may say, oh, this minus this 5. Well, be careful. Remember, we're not looking, time doesn't have direction. But over here, we're not so concerned with which comes first. We need to actually still use our brains and say, what's happening? If Husky took 5 seconds longer, that means Steady has to be 5 seconds less than 13.3. So 13.3 minus 5 is 8.3 seconds. And finally, the question is, we wanted to know, let's see, how fast is Steady cart? So we need this right here. V bar is D over T, which is 2.0 meters over 8.3 seconds. So 2 divide 8.3, you get about 0.24. 0.24 meters per second. And actually we're done. That's all they asked for. There's Steady's speed. Okay. Well, pause if you need to, but I'm going to keep on trucking. All right. Brandon decides it's time to freshen his look. He rocks that finest Supreme marker, follows Christine to the tanning salon. Okay. It's a chase situation again. Christine's walking at 1 meter per second, Brandon's walking at 2 meters per second, and to catch up, he's starting behind. How long will it take him to catch up? All right, so we got Brandon, we got Christine, we got relative, V bar, D, and T. Let's see what's going on here. So, there we go. I got that Thursday night. So, let's see here. Christine is walking at 1 meter per second. All right, thank you, Christine. Brandon is walking at 2 meters per second. All right, thank you, Brandon. Now, Brandon begins 200 meters behind. Hopefully at this point you're starting to recognize when one begins behind and then they catch up. That amount they begin behind, that 200 meters, well, number one, we focus on that because it's the easiest thing to know ahead of time. You start here, I start here, how far apart are we to begin with? That's actually your relative displacement over here, 200 meters. Okay, how long will it take him to catch up? Oh, we don't have enough yet, but we can get the relative speed. So he's making chase, going 2 meters per second to 1 meter per second. So the relative speed between them is 1 meter per second. They're both going in the same direction. Aha! Now we can get time. Time, of course, is D over V bar. So 200 over 1 is just 200 seconds. That's pretty easy. Now they're both walking for the same amount of time. So then they are all doing 200 seconds of time over here. All right, and now let's figure out the, oh, we're done. We don't need anything else to figure out. 200 seconds, there's the answer. Good. One more. And this is the one that I have special fondness for. This is one of those Grandpa sits you down at the diner and says, all right, I want you to think about this and figure it out. And you usually don't. Anyway, we have two trains. 800-mile separation. One in New York City, one in Chicago. Thomas the train leaves Chicago, heads east toward New York at 80 miles per hour. Speedy Spencer the train starts out in New York City and heads west at 120 miles per hour. How long until they meet? Also, what's the displacement of each train from its start? Ooh, okay, we got some questions here. Well, notice you have two objects coming toward each other. They're not coming at the same rate, so they're not going to meet just smack in the middle. We know the distance between them to begin with, so that should tell you something. Let's see what. So, we got Thomas, we got Spencer, we got relative, V bar, D, and T. Thomas the train prefers blue, so we're giving him blue. All right, so Thomas is heading east. Now this is a big deal. East at 80 miles per hour. East! We may want to establish that east is positive. That's going to come into play here. So Thomas is heading our positive 80 miles per hour, not meters per second. Miles per hour, only be about 40 meters per second. 80 miles per hour. Spencer is heading west. Spencer, I know, kind of likes gray. All right, Spencer. Spencer's heading west. Now, west actually is the other way, which means west must be negative 120 miles per hour. Now, this is relevant. We talked about this in the video with the speed guns, but the relative speeds, you got to be careful. Now, if they're chasing each other, the relative speed is a subtraction of the two. If they're approaching each other, the relative speed is still a subtraction of the two, but you got to keep track of the fact that one is going in the negative direction. So, the resultant speed, tractor, the resultant speed is 80 minus 120, which is 200 miles per hour. And that's not crazy. They're both coming toward each other, which means the distance between them is disappearing more rapidly than if they were chasing or moving apart. So, or if even one were sitting still. So it makes sense that it's actually a greater relative speed. If they were to collide, you have greater fire and brimstone. All right, let's keep going here. Now that 800 miles between them, that's that relative. It started out at 800, it's going to end at 0 when they meet. So there's your relative D, 800 miles. Okay. Oh, we can get time. Let's do it. Time is D over V bar, which is 800 miles over 200 miles per hour. 800 over 200, you get 4 hours. And they're all driving this 4 hours. So a little bit of inconsistency rather in the way the time row plays out. Sometimes it's a subtraction, sometimes it's just the same across. Use your brain. This is not that cut and dry, but it does clean it up. They're both driving for that amount of time, so they are all getting the 4 hours. Okay, good. So how long until they meet? Well, that's done. Then, what are we going to do over here? Now, we need to figure out, all right, D for Thomas, which we'll do in Thomas's blue. D is V bar times T, which is 80 miles per hour times 4 hours, and that gives you positive 320 miles. That means Thomas is 320 miles east of Chicago. At the same time, Spencer, since they are meeting, they will be at the same location. We could do the same little math over here. So that's 120 negative times 4 hours will give you negative 480 miles, which just means 480 miles west of New York City. These, of course, are the same location. So the displacement of each train, well, 320 miles east of its start, 480 miles west of its start, and boom, there it is, relative motion in a pretty clean presentation. If you didn't like this that much, trust me, the other way is worse. Now get that pen relatively moving towards your paper and do some work.